Hello. We are going to start a new chapter, chapter 5 about binomial distribution. So this chapter, from now on, from chapter 5, we are so the first four chapters, we learned how to summarize data, or how to describe and characterize the data. But from now on, we are going to consider some assumptions. So when you calculate a probability or a mean, you don't need any assumption. Maybe the only assumption is that the random variable is numerical, which is not actually an assumption. It's quite mild restriction. So, but from now on, we are going to make assumptions and we will set up a statistical model. So in general, a scientific model means a simplification of phenomena using assumptions in any science, in economics, in statistics, like in physics, whatever. A model is a set of assumptions that make that explain phenomena or whatever you want, and under the assumptions in a simpler way. So it simplifies what you observe and explains within the assumptions. In statistics, yes, we are doing similar things. In a statistical model, there are assumptions, and under the assumptions, we have a few parameters that can describe the full distribution. So, in the previous, in the previous chapters, in probability or mean, one of the important thing there was we would like to summarize the data. But when you summarize data, uh, there are some information lost during that process. So when you calculate the mean, you are losing the information about variability or asymmetry. When you calculate a probability, you need to calculate other probabilities to understand the full shape of the distribution. So like that, when you summarize the data, you are losing informations. But now we are doing a different approach. We make assumptions. So under that assumptions, we do not lose any information. Still, we may summarize the information into a few parameters. Then the issue is whether the assumptions are plausible or acceptable in your application. If the assumptions are reasonable, then it's a better way to study the distribution. So we are going to in this course we are going to study two statistical models, distribution models. In chapter 5, in this chapter, we study the binomial distribution, and in the following chapter, we study the normal distribution. So these are two uh, most common distributions, so I only included them. The relevant chapters in the textbook are these. The keyword is binomial distribution. So, like whatever textbook, just search for binomial distribution. Then you will find a similar content. Before heading into the main part, let's think about a simple question. I give you five examples, five random variables, and one of them is different from the others. Think about this. What is that? The first random variable is the outcome from a coin toss, and the second is gender of a randomly chosen person, and third, whether a randomly chosen student has a passing grade in calculus or not, and D, the price of a randomly chosen dish on the menu, and finally, answer to a true false, say, exam question. What is a different variable? The answer is it's not a serious question, I want you to think about this and see what's common and what's difference. What's the difference? And the difference is D. The different one is D because all the others are binary. Outcome from a coin toss is head or tail, and gender is male or female. Whether you have a passing grade or not is pass or fail, and answer to true false question is either true or false. So, but in the answer D, the price of a randomly chosen dish is not a binary. It's not yes, no, or true, false, or head or tail thing. So price can take any positive number, but the other four can take only two possible values. It's quite common. This kind of uh, random variable is common in many applications in many analysis, like yes or no, true, false, right, wrong, man or woman, head or tail, good or bad, blah blah blah. So this is the starting point. We are going to make an assumption based on this uh, property, this nature. So we say a random variable is binary if there are only two possible outcomes. So like all the examples like man, woman, yes or no, true or false, head or tail, all of these have only two possible outcomes. And in general, in our model, we are going to take this as an assumption. And just in general, we call them success and failure. There are two possible outcomes, success, and we call them success and failure. But I'm not saying success is a good outcome and failure is a bad outcome. It's just name. They are just names, and I'm not saying what is better. And also, we will, when needed, we will usually we label success as 1 and failure as 0. So you can think success is another name for 1, failure is another name for 0. So it doesn't mean 1 is good and 0 is bad, right? So like later on, I will just say success or fail. And examples, as I said, a lot of examples: man, woman, or yes or no when I ask you a question, and true or false, win or lose when you play something. The result is another binary random variable. Positive or negative, like when you get a test for the coronavirus, the result is also binary. It's positive or negative. So there are a lot of examples uh, you can think of as a binary random variable. So then so we are going to restrict our focus, our attention only to binary random variables. And in a general notation, we are going to use x as a binary random variable. And by definition, by assumption, there are two possible outcomes: x equals to 0 or x equals to 1. And then what we need is only two probabilities. The random variable is perfectly described by two probabilities. If you know probability of 1 and probability of 0, then you know everything about this random variable. And also additionally, implicitly, what we know is that the sum of these two probabilities must be always 100% because there are only two probabilities, two outcomes, excuse me, two outcomes. So that means I am going to denote the probability of 1 as p. So this p is my notation, like general notation. Then you don't need to put another unknown for the other probability because the other probability equals to 0, becomes 1 minus p automatically because sum of probability of 1 and probability of 0 must be 1, right? Therefore, when you have two possible outcomes, actually what you need is just one probability. There are two probabilities, but if you know one of them, then automatically you know the other. So that's you are not losing any information if you know this one number. If you know this probability, you are good. You are not losing anything. Or the probability distribution table can be written in this way. Outcome is 1 or 0. Probability is either P or 1 minus P. P and 1 minus P. And what you need to know is P, one number, P. P is a parameter in this model. So let me summarize. A binary distribution requires these two basic assumptions. X takes only two possible values, 0 or 1, and we say we are going to denote the probability of 1 equals to P, or probability of success equals to P. That's it. If you have these two, if a random variable satisfies these two assumptions, then the random variable x, we say the random variable x follows a binary distribution or Bernoulli distribution with parameter p. Bernoulli is a statistician who made this theory. So anyhow, I'm going to call this binary distribution because that's more intuitively understood. So x follows a binary distribution with one parameter, p, and mathematical notation is x wiggle binary p. So wiggle means x, random variable x has this distribution, follows this distribution. So you can read it as x follows binary distribution with parameter p. This is what we are going to study. And in more general view, I would say this: if an experiment or a random variable satisfies certain assumptions, then there may be a few parameters, a small number of parameters that can fully characterize the distribution. Then we say these all the distributions that satisfy those assumptions make a family of parametric distributions. So parametric distribution family. So all distributions in that family satisfy the same required assumptions, like binary distribution model. But still within, even if they satisfy the same assumptions, but the distributions may look different. The shape of their distributions can be different depending only on the value of parameters. So in this example, P is the probability of success. It can be 10%, it can be 50%, it can be 90%. So depending on the value of P, the distribution would be different. However, still all of them are binary distribution family. So all of these, like all these examples satisfy the binary distribution assumption. So they are all binary distribution family, but the probability of success will be different from an example to another. Still, they are a family. Okay, we learned so some other examples of parametric distribution families that I do not cover in this course are Poisson distribution, exponential distribution, gamma distribution, and many more. Many more distributions are important but not covered in this course. So if you are interested, if you're seriously interested in statistics, you may take mathematical statistics course where you can learn more distribution models. They are interesting. So because these are commonly used models, then you can find examples, a lot of examples in daily life that satisfy these assumptions. Okay, I'm going to stop here and see you in the next video.